we're going to look at what are called limited dependent variable models. These are models where the outcome variable is observed in a limited way. That's why it's called limited. So you don't see the outcome variable for everybody, but you might see it for some people. Okay, and the main reference for this material is the Amemiya textbook. All right, so discrete choice models could be thought of as limited dependent variable models, because we only observe the choices that are being made and we don't see exactly, say, the utility they got from a particular choice. Okay, but there are many other situations that don't fall within the discrete choice setup. Okay, so let's look at models from James Tobin. Okay, and I think he actually won the Nobel Prize. And these models are called Tobit models, so it's actually named after James Tobin. So in this example, people are purchasing a durable good, but you only see the price that they're willing to pay if they actually buy the good. So we assume that there's some minimum price in the market, which is, let me turn on the pencil here. Yes, so that's the minimum price in the market, Y0. Okay, and so they only buy the goods. So you see the price they're willing to pay if the price is above the minimum price. Okay, or you can write it this way here. Now, how do you estimate this kind of model? Well, we're going to consider both parametric and some semi-parametric methods later on in the course. But for now, let's consider a parametric method. Assume that the residual is normally distributed, mean zero, variance sigma square. Okay, so yi star, so the star means it's latent. Okay, that's every time you see a star, think of it as that it's not fully observed. Okay, we observe di equals 1, which means they purchased the good. Okay, if yi star is greater than or equal to y0. So we can write the likelihood. So the likelihood is going to be the probability of observing what you did observe. Okay, so for people with di equals 0, so they didn't buy the good, what do you know about them? Well, you know that their willingness to pay was below the minimum price in the market. Now, for people with yi greater than y0, for them you actually see how much they were willing to pay. So you have more information on them. All right, so now we can write out what are these probabilities, given that we assume that UI is normally distributed. So this probability here, right, the probability that the willingness to pay is less than Y0, so you move everything that's observed over to the right side, so you get the probability that UI over sigma U is less than Y0 minus Xi beta over sigma U. And then given the normality assumption, this is going to be a normal CDF. Okay, now the probability, or sorry, for the people that actually bought the good, you see what yi star is, So you see more, so we need the density. And it's a conditional density because it's conditional on having purchased the good, which means that yi star is greater than or equal to y0. So this is the conditional density. Okay, note that the denominator here is actually this probability. And this density integrates to 1. All right, so you can write the likelihood in this way in 2 different pieces, which sort of emphasizes the different pieces of information we have. Okay, so this is the probability of not buying the good on this side, and then this is the probability of buying the good. And you can see that for the people that bought the good, you see the density, and these things actually cancel out. It's just written this way kind of so that you can see the information. So if we only did a probit model, did you buy the good or not, you could only identify beta over sigma. You couldn't get the two separately. As we discussed before, the beta is only identified up to scale in a probit model. But if you have the additional information on the actual, price they paid given that they bought the good, you can see you can actually identify the sigma u. Okay, so having this additional piece of information actually gives you more identification. All right, so the first two products, I think I already said this, but the first two products just show what you can get from a Probit model, okay, and then the additional information, you can actually estimate sigma u, which is not otherwise identified from the Probit model. All right, now let's look at a truncated model. So this type of model is called censoring. Okay, and the reason is that we're assuming that you observe things about people that did not buy the good, right? We're assuming that for people that didn't buy the good, you see their excess and you see that they didn't buy the good. That's called censored data, okay, censoring. Sorry, it's hard to write on this screen. Now, the other type of data you could have is truncated data. So truncated data would mean that you only observe information on people that actually bought the good. You observe nothing about people that didn't buy the good. So for example, suppose you collected your data at the appliance store or something, and as people were checking out, you interviewed them. So then you'd only have information on people that bought something, right? So in that case, you have less information, and all you have is the conditional likelihood, okay, or the conditional density here, because you only observe information on di equals 1. It's still possible to estimate the model parameters. So what's the trade-off? Well, it's efficiency, basically. It's going to be less efficient to only use this information, but you can still estimate the model with only censored data. Okay, so different ways of estimating Tobit models. So MLE. So MLE usually has the advantage of being efficient. Usually I think of MLE as the best method. When I can do it, I try to do MLE. But if you have censored data, you can also adopt a two-step estimator, which I guess people used to use two-step methods a lot more for computational simplicity. But computers are a lot better nowadays, so it's usually not that hard to do MLE directly. But I will describe, how you can do like a two-step approach or a nonlinear least squares approach. Okay, so the two-step approach. So the first step is you estimate a Probit model only using data on whether the good is purchased. Okay, and from that, you only get beta up to scale. Okay, so this is step 1. So step 1 is this. Okay, now step 2 is you estimate this regression, but it's conditional on having purchased the good. Okay, so we capture this conditioning through this set here. So this is E of ui given xi beta plus ui greater than or equal to 0. This is not equal to 0, this term, right? Because we're only conditioning on people that bought the good. People that bought the good will tend to have high UIs, because they had a high willingness to pay. So you can't just ignore the fact that you're conditioning on people that bought the good, right? So, but Heckman, okay, these are some of the papers Jim Heckman is famous for, is he showed how to statistically control for this type of selectivity. So in this case, the selectivity is we only see people that purchase the good. And we can write out, this is called a control function approach. So we're actually going to find a function for this, okay? So we can write this, so first of all, you can normalize this, okay? And then I usually try to normalize everything so that everything is, if you divide by its standard deviation, then it's normal 0, 1, So we need to find a regressor for this object. Okay, so, and to do this, we're going to use some properties of truncated normal random variables, okay? So if you have E of epsilon given epsilon is greater than or equal to C. So that's a normal random variable truncated from below, that's truncated by C. Okay, so you can think of that as like if you had a normal distribution and you took a bunch of draws from the normal and you set some truncation point C, and then you only take the mean of the draws that were above C. That's what this is. E of epsilon given epsilon greater or equals C. And if it's normal without the truncation, like normal means 0, then it's going to be normal with some positive mean with the truncation. Okay? So the formula, and I'll just give you these formulas because, I mean, there are, I think I have some derivations somewhere, but it's a bit of work to derive these things. But this is a formula for truncated normal random variable. Okay? So the numerator here is the density, and the denominator is the probability of this. Okay. Oops, sorry, which is 1 minus cap phi, and that using the symmetry of the normal. Sorry, I didn't mean to make this thing in here. Okay. Now truncation from below. So alternatively, if I have a normal CDF, right, and then I set some truncation, and then I only take the means of the ones below, that'll be negative, because without truncation it has mean 0, with truncation it'll be negative. So this is the formula, and again the denominator is the probability of this event. All right, and these expressions are known as Mills ratio, and this comes up sometimes in actuarial analysis. So actuarial is like applications related to insurance. So when they were doing like life insurance calculations, they might want to know like the expected length of time that somebody's going to live, given that they already live to be age 65, things like that. So you have these sorts of truncated random variables. I mean, we'll look at a few different, because we're also going to look at the Roy model, so, and that uses similar formulas. So I would just commit these formulas to memory because you'll definitely see them again in different contexts, okay? This also comes up in survival analysis. So I would just, memorize these formulas for truncated normal random variables. Okay. And this is called the Mills ratio, and it's usually referred to as lambda. Sometimes they might call it like the lambda function. Okay. So now let's go back. So we had this. So now we have an expression for this here using the Mills ratios. Okay, so the idea is you first estimate beta over sigma u by probit, and then you can form this lambda, okay? And it'll be lambda I hat because you don't know the actual beta. You're putting in an estimate. So technically, the difference between the true lambda and the lambda hat is going to go in the residual, okay? Actually, the sigma, I guess, should have a u on it because it's actually the same as this one here. Okay. Well, nowadays there's software that does a lot of this for you. Like in Stata, there's a Hecate procedure, and in R, they also have some packages that will do this for you, okay? One thing to note is there's going to be heteroscedasticity because of this term. Okay, but adding in the control function means that the residual then has conditional mean 0. So it's controlling for the selectivity. The error term composite error will be heteroscedastic, which means you couldn't use weights to improve efficiency if you wanted to, or you'd have to use some sort of like robust standard error calculation. This is also something called an estimated regressor problem, right? Because we're sticking in an estimated regressor from a first stage, and it's also sometimes called the Durbin problem, okay? So how do you get correct standard errors? Well, there are a couple of different methods. In Heckman's original article, he suggested just using the delta method. Or Newey has a short little paper, which is very elegant. He shows how you can set this up as a GMM problem, where the moment conditions are the conditions from the regression combined with the conditions from the first order condition from the probit model. Okay, because the first order condition from the probit is a moment condition. So if you use those two moment conditions at the same time with the optimal weighting matrix, that would just, give you the correct efficient standard errors. So that's a nice little paper, actually. Economic Letters, they publish things. Well, the reason I say little paper, it's like they publish a lot of papers that are short, kind of like notes. Okay. Or, I mean, this Hackett procedure in Stata and the procedure in R, they both do the correct standard errors. So it's not that crucial. It's good to understand exactly how the procedure works, but usually you can get software to do the standard errors for you. Now, another way, so far we did two methods of estimation. So MLE, two-step method, and another approach is you could do nonlinear least squares. Okay, so if you say, what is E of y given x? So this is using all the data, including the zeros. That's going to be the probability that you don't buy the good times 0, plus the probability you do buy the good times the E of y given you bought the good. Okay, so this would be, if you ran a regression, just using the all the data, including the zeros, this would be the conditional mean. So you could estimate this model replacing this phi by phi hat and lambda by lambda hat and do nonlinear least squares. Okay, so that's just the simple type 1 Tobit model. So let's look at the type 2 Tobit model. So in the type 2 Tobit model, the difference is we have a different equation describing the outcome and whether the outcome is observed. And so here you can see we see y2 if y1 crosses a threshold. Okay, so whether or not you see y2 is determined by y1. So it's just this, in the previous example, we see y1 if we see y if y greater than y0. But here we see y2 based on the value of y1. So you can see it's a little more general. Okay. So how would we set this up in terms of the likelihood? Well, for the ones where you don't see y2, you just know that y1 was below 0. Okay. And for the ones where you do see y2, this would be the likelihood. I mean, it's really going to be the joint probability, but one is discrete here, whether or not you see y1, and then the value of y2 given that you see y1. Okay, and we can write the value of y2 given that you see y1 in this way. So this is the joint density of y1 and y2, and then we can write this as taking out the marginal density of y2, and then this is the conditional density here. Okay. All right, and then if we make a normality assumption, I mean, in this chapter in Amemiya, it's basically parametric, and a lot of Tobit model analysis is parametric. You don't have to assume normal, but normal sometimes is convenient, so that's why a lot of these are just assuming normal. Okay, so we're going to assume that the two are normal. These are conditional densities for one normal random variable conditional on the value of another. Okay. All right. And I mean, I have to look these up normally. I don't have these memorized, but once in a while you need to use these types of formulas. Okay. So by MLE estimation. So this is the part for people where you don't see y2 at all. Okay? This is the probability you do see y2, so that's that y1 exceeded 0, the y1 star, this here. Notice that this here is canceling with this. Okay, so this actually cancels with this. And now this y2 star, this density is this here. And now this part here is here. Okay. All right. Okay, and if you look closely at the likelihood, sigma 1 never enters by itself. It only enters as beta 1 divided by sigma 1. And then also we have sigma 1, 2 never enters by itself. Okay, so we cannot separately identify sigma 1 because we never actually see y1. We just see whether y1 star is greater than 0 or not. So that's why you cannot identify sigma 1. So without loss of generality, you can impose a normalization like sigma 1 equals 1, and then you can identify everything. So, I mean, if you try to estimate something where not everything's identified, that means you'd have multiple solutions, and then your, optimization procedure would never converge. That's how it would show up. Okay, now by a two-step approach. So this is the MLE approach. Let's look how you do this by a two-step approach. So you need E of y2 given y1 star is greater than 0. Okay, so here, this is the mean of one normal random variable conditional on the value of another normal random variable. Okay, and that's going to be sigma 1, 2. They're both mean 0, so this just could be sigma 1, 2 over sigma 1, because this cancels with this. And then E of this one conditional that that's greater than this. And there you can apply these Mills ratio formulas to get that as truncation from below. Okay. So, and then the alpha, when you estimate this regression, alpha will be equal to that. Okay. But you do this in two steps normally. So the first step is just, is y2 observed or not? That'll give you beta 1 over sigma 1. And then you can form your Mills ratio. Okay, and then you can estimate the second stage regression, including the Mills ratio. Okay. So this is an example. This is kind of more related to my research. Suppose we want to estimate the effect of school quality on school-going behavior and on test scores. Okay, and a lot of times tests are only given in school. So you only observe test scores for the kids who actually go to school. Okay, and there's a big literature that relates, like test scores to school quality. But a difficulty in developing countries is that if school quality is very low, kids may not go to school at all, and then you wouldn't even see their test scores because the tests are actually given in school. Okay, so how would you measure quality? Well, I mean, in the US, it's normally like pupil-teacher ratios, teacher certification, like whether the teacher has master's degree, things like that. But in the developing countries, sometimes other things are relevant, like whether the school has a roof, because some schools that don't have roofs, if it's raining, they can't have school, so problems that we don't usually have here, but whether the school has a bathroom, because there are a lot of countries where a lot of like adolescent girls don't want to go to school because there's no bathroom. So these are important variables for some context. Textbooks in the school, because some countries have a lot of shortage of textbook. But then all countries pretty much measure like teacher characteristics as a measure of quality. Okay, so how does this fit within the Tobit model framework? So Y2 would be test scores, and Y1 would be the index about whether parents enroll their kids to school. And so you only see Y2 if the child is enrolled in school. Okay. And there could be some variables that enter into Y1. I mean, actually, I didn't talk so much about exclusion restrictions, but see here in this regression, ideally, you do not want x2 to equal x1. Because if they're all exactly equal, then the only reason you're able to separate out these things in a regression is from functional form. That this is this lambda function and that's a nonlinear function. Sometimes the lambda function can be close to linear, and so it kind of creates some collinearity problems. So people don't normally like it if all your identification, say of beta 2, is based off of functional form. So ideally you want to have some variables, say in x that are not in x1 that are not in x2. And those variables are called exclusion restrictions. Like they enter one part of the model, but they don't enter another part of a model. Okay? So in this example, something like distance to school, that could affect whether a child goes to school, but does not necessarily affect test scores directly. Okay, so ideally you'd want to incorporate some sort of exclusion restrictions into your model. Okay. All right, now this is a different example, but this is also fits within that similar Tobit model framework. And this is actually related more to Heckman's original analysis when he first proposed this two-step method. He was actually building on this grow now female labor supply model that he then extended. Okay, and I don't know if you ever took a course in labor economics, like even at the undergraduate level, you cover this model, which is, so this is leisure, this is consumption. Sorry, I can't draw that straight. This is non-labor income, usually V. Oh, here I called it A. Let's see. That should be A. Okay. And leisure 1 is maximum leisure. So that would be if you took all leisure and didn't work at all. Then your consumption would be A. Okay, and the slope of this line, this is your budget set. The slope is minus your wage. W is your wage rate. Okay, and let's assume that people have some sort of utility function over consumption, leisure. And the tangency, you know, if they're working, then you'd expect to see this tangency, that the marginal rate of substitution equals the wage. If they're not working, then it would be like this, okay? And that means that the marginal rate of substitution is greater than the wage. Okay, so they'd like to even take more leisure than they're taking. Okay, and this is really like at L equal 1, H equals 0. Okay, and this is defined as the reservation wage. The marginal rate of substitution at full-time leisure is the reservation wage. Okay. So in reality, you do not usually observe the reservation wage. You know, there are a few data sets that maybe ask people, like, what's the minimum wage you'd be willing to work at? But usually we don't have that. So we normally specify a model for the reservation wage. So that's here. And you observe the wage if the wage offer exceeds the reservation wage. Okay, so if you set Y1 to be the difference between the wage offer and the reservation wage, and Y2 to be the wage offer, then you get this Tobit model, this type 2 Tobit model framework. And if you have some variables that affect the reservation wage that are not in the wage, then those are exclusion restrictions. Okay. Now, Heckman actually extended Gronow's original model, and the extension was partly to say, well, in reality, usually we don't just observe the wage, we also observe hours. So he incorporated hours into the model. Okay, and so what he did is he wrote down this utility function. So I don't actually have all that written out here. But the utility function implied a marginal rate of substitution of this form. Okay, and so at hours equals 0, this is the marginal rate of substitution. Okay. And this led to a Tobit model. So if a person works, their wage equals the marginal rate of substitution. And this then also implies an equation for hours. Okay. So we observe both hours and wages. So we observe two outcomes based on whether the wage is greater than or less than the reservation wage. So the Y1 is the same, Y2 is the same, but now we also observe, well, Y1, yeah, it's still hours, whether it's greater or equal to 0, but now we actually partially observe hours. Okay, so if they're working, you see Y1, and you see Y2. And if they're not working, then all you see is they're not working. Okay. All right. So the type 4 Tobit model, well, let's see, this is type 3 Tobit model that also incorporates choice of H. Now let's look at type 4 Tobit model. And I guess these different Tobit models, you can write down Tobit models that don't fit within any of these types. Okay, I think they were kind of motivated by early applications, some papers that applied these sorts of models. Type 4 Tobit model just adds another equation that you observe based on Y1. And you can estimate these models again by maximum likelihood or by like two-step method. And as the models become more complicated, then it might make sense to do like a two-step estimator because it's simpler to implement, because you can just do that with regression analysis. Okay, now this is kind of a famous model, and this is called a type 5 Tobit in Amemiya's textbook. It's a switching regression model. Okay, so there are two equations for outcomes. Okay, there's Y1 determines whether you see either Y2 or Y3. So you always see either Y2 or Y3. But which one you see is based on Y1. So it switches in between those two. Okay, that's the setup. So if Y1 is greater than 0, you see Y2. If Y1 is less than 0, you see Y3. Okay, and for Y1, you don't see Y1, so you only see the sign if it's greater or equal to 0. All right, there's actually a very big literature, like the whole treatment effects literature is sort of based on this, because Y1 or Y2 and Y3 would correspond to like receiving treatment and not receiving treatment. Okay, and then there might be some model for who gets allocated to treatment. Okay, so we can write the likelihood if we assume that the residuals were all from a trivariate normal distribution. You can write out the likelihood in this way. Okay. Here. So here's an example of how that model could make sense. And this is a very famous model. Lee was studying the effect of unions on wages. Okay, so you see wages either in the union or not in the union. So it's kind of like treated or not treated, where treatment is being in the union. Okay, but the decision to be in the union might depend on, how much it boosts your wages. So the decision to join a union, so a union, is like a bargaining unit, so that the workers bargain with the firm through this unit, like bargain. In many countries, unions are important. In the US, they used to be very important, although in recent years, they've kind of declined in the US. But so this is the anticipated benefit from being in the union. And then there might also be some other factors, monetary or psychic. A lot of times they charge dues to be in the union. I guess, I don't know, some universities have even a grad student union. I'm not sure if Penn has it. Well, I think every once in a while the grad students vote whether to be in the union or not. Okay, when we look at the Roy model, this is very similar to the Roy model setup that we'll look at later. Okay, and then this is the last example here. This is another paper by Heckman. It's kind of like another Tobit model. Depending on your structure, you can get like different Tobit structures. But you see that all of these have some latent variable that's not fully observed, right? Like in the union example, you only see union wages for people who join the union. Okay. So here, this is, he was estimating the effect of anti-discrimination laws on income of African Americans. Okay, so this was in 1978. So you see, we're still dealing with similar issues in the U.S. So Y2I is average income of African Americans within a state. Y1I is unobserved sentiment. So this would be like discrimination towards blacks in the state. And then WI is whether there's a law or not. Okay, like whether there's a law prohibiting discrimination. I mean, nowadays most places have laws, but I guess the data he was using was, they didn't all have laws at this time. Okay, so here so Y2 is income. Sorry, the notation is hard to remember, but Y2 is average income of African Americans within the state, which could depend on whether there's a law, and it could also depend on just, unobserved sentiment. That would be like maybe there are a lot of firms that discriminate, and then also the anti-discrimination law could have an effect. And then this is the unobserved sentiment, which is, unobserved, so that's why it has the star. Yeah, and so that unobserved sentiment, maybe the law could also affect sentiment. Like if you have a law in the books, that might actually affect the way people feel about, discrimination or something. Okay, but he showed that in order for this model to actually be coherent, you had to impose some restrictions. And he showed if you solve for yi, the solution should not depend on w. So you couldn't estimate this model the way it is. It's actually logically inconsistent. You'd have to impose some restrictions on the coefficients. Okay, so I mean, all of these examples are discussed in Amemiya's chapter, so it would be a useful supplement to these notes to also look at his chapter.